All right, let's look at the practice exam 3, problem number 5. All right, so let's use L'Hopital's rule to evaluate these limits. All right, first one. And if you, first thing you plug in, you can see that here, the denominator, 0 squared is 0, so denominator goes to 0. And 3 times 0 is 0, 1 minus e to the 0 is 1, so 1 minus 1, 0. So the numerator also goes to 0. Right? So since you have 0 over 0, we can apply L'Hopital's rule. So let's apply L'Hopital's rule here. Right? So we still have this limit, but L'Hopital's rule said that we can take the derivative of the numerator and the denominator separately. So derivative of 3x is 3, and derivative of 1 is 0, and you have a negative sign, and derivative of e to the 3x would be e to the 3x, but because of the chain rule, multiplied by derivative of 3x, so that's going to be multiplied by 3. Right? Derivative of x squared is 2x. Right? Then plug in. Right? 2 times 0 is still 0. Right? And 3 minus 3 times e to the 0 is 3 minus 3, so still the numerator goes to 0. Right? So we can apply L'Hopital's rule. We don't have to stop. We can apply L'Hopital's rule as many times as we want, as long as if you have 0 over 0 or infinity over infinity. So x goes to 0. Right? So derivative is of 2x would be 2. Derivative of 3 is 0. Right? Derivative of negative 3 e to the 3x would be, right? So negative 3. Right? Derivative of e to the 3x would be e to the 3x times 3. So I'm going to change that to, this is going to be 3 times 3, so it's going to be 9. Right? Then as x approaches 0, e to the 0 is 1. So this guy approaches 1. Right? So therefore, what's left is negative 9 halves. Right? So that's part A. All right, part B. All right, if you plug in x goes to infinity, so you can see that the base is approaching 1, right? But the power is approaching infinity, right? 1 to the infinity is one of the forms that L'Hopital rules applies. So let's do that. But in order to apply L'Hopital's rule, we need a fraction form or a quotient form. So the trick is this: we can do, okay, so we need to take the limit x approaches infinity. Then we're gonna do e to the natural log trick, right? Then because the e to the exponential function and the natural log functions are inverses of each other, so essentially basically they cancel out each other. So you have 1 plus 1 over x raise it to the x power, right? And what we can do is we can actually move this power in front here, right? But so I'm going to just scratch that out and put x here, right? But the multiplying by x is same as dividing by its reciprocal, so I'm going to write it this way, since I want in a fraction form or a quotient form. So we can write it as, okay, you have a natural log of 1 plus 1 over x, right? Then multiplied by x is same thing as divide by 1 over x. Right? Then you can see that here, as x approaches infinity, this guy, denominator, approaches 0. Right? And of course, this guy approaches 0. So you have a natural log of 1, but the natural log of 1 is 0 as well. All right. Now we have L'Hopital's rule. So this is, again, apply L'Hopital's rule here. Right? Then I'm going to also squeeze this limit inside the exponential function. since exponential function is a continuous function, we get to do that. So you have a e to the, right, you have a limit as x approaches infinity, right? Then we take the derivative, so applying L'Hopital's rule. So derivative of 1 over x is negative 1 over x squared, right? And derivative of natural log of 1 plus 1 over x would be, put the 1 plus 1 over x on the bottom, take the derivative of that, which is negative 1 over x cubed, on top, right? Then we can actually cancel negative 1 over x squared here and a negative 1 over x squared, so you just have 1 left, right? So the limit is, maybe I'll clean up a bit, so you have e to the limit as x approaches infinity. Then what you get is just a 1 over 1 plus 1 over x, right? But we know that 1 over x approaches 0 as x approaches infinity. So you have a limit is going to be 1 over 1. So it's 1, but you are raising e to that. So e to the 1, which is just a e. All right, that's it. I hope that this was clear.